So we've derived the SVM dual so far. It's a dual that you always see kind of in basic ML class. How about the Lasso dual? Another common problem we see. What's the dual of the Lasso problem? Let's go through the steps, and we'll find out that actually, once we know conjugates, they play a role here in deriving the dual. So we're going to see also here an example of a trick we have to play in order to get a dual. So the Lasso has no constraints if I write it this way, in Lagrange form, penalized form. And so what is the dual function? The dual function is given by minimizing this overall beta, right? Plus the Lagrangian terms, but they're vacuous because there are no constraints. So the dual function is actually a constant. It's a function of no variables, and it's equal to a constant, which is f star, the optimal value of this problem. Not very useful, right? If we didn't try anything else, we might have given up and said that the Lasso dual is just not interesting. In fact, the dual of any unconstrained problem is just not interesting. But that's actually not the end of the story. What we can do is transform the primal problem to an equivalent problem that has a constraint in order to get a dual out of this problem.
Excuse me, you said that due to what function is constant? It's due to the whole function.
The Lagrange dual function for this problem is a function of no variables, because there are no constraints. And everywhere it's equal to a constant, which is f star. That's true because it's defined by minimizing the Lagrangian over all primal variables. But the Lagrangian is the criterion itself, because there are no constraints. Yeah?
By f star, you mean you don't mean the conjugate of that, you mean the optimal value?
Yeah. So this is not that clear, but I'm actually using like an asterisk for conjugate and a star for f star. So this is supposed to be, see an example. See? But yes, I mean the optimal value, not the conjugate. Sorry. So maybe, I'm not sure what we're going to do except for maybe just kind of by context, maybe it would make sense. Yeah, Han. That's possible, but this is actually a better route. So we'll get a better problem out of this, one that makes more sense, more traction, like for the Lasso problem. So we're going to introduce, and this also applies to just kind of arbitrary, unconstrained problems, the strategy. So we're going to stick an inequality constraint in here, and we're going to say I'm going to replace x beta in the loss with z. I'm going to introduce the constraint that z must be equal to x beta. Okay, so kind of trivial modification to the problem, doesn't change the problem. But now I actually have a constraint, and I can derive a dual function. So I'm going to let u be the dual variable corresponding to this constraint. So it's n dimensional because I have n constraints here, right? If x is an n by p matrix. And the dual function is given by minimizing the Lagrangian, which is the criterion, which is a function of now beta and z are my primal variables, plus u transpose z minus x beta. So let's write out this in slightly more detail. The Lasso problem is given by y minus z squared plus lambda times the L1 norm of beta plus u transpose z minus x beta. And the dual function is now a function of u, and it's given by minimizing the Lagrangian over beta and z. And let's group this into two separate minimization problems because z and beta actually decouple. So I can write that as the minimum overall beta for all the terms that involve beta. That looks like this. It's lambda times the L1 norm of beta minus x transpose u transpose beta plus, write it over here, the minimum overall z of all the terms that involve z, and that's just this, plus u transpose z. Okay, so this one you can do explicitly because it's a quadratic. So I won't go through that. Just take the derivative and set it equal to 0, the gradient set it equal to 0, or just do what you remember for the minimums of quadratics. And this ends up equaling, the minimum equals the following. 1/2 the norm of y minus 1/2 the norm of y minus u squared. What about this one? Looks maybe complicated, right? Requires us to pull out subgradients or something because the L1 norm is in here. It's convex, but it's not smooth. Forget about that. Let's not do that. Let's actually recognize this as something to do with the convex conjugate of the 1 norm. So let's just rewrite this as minus the maximum overall beta. In fact, I'm going to write it as minus lambda times the maximum overall beta of the following: x transpose u over lambda transpose beta minus the 1 norm of beta. I've not changed anything. I've just pulled out the lambda so I get the 1 norm as I wanted. And I've changed the sign so that I can write this in terms of the conjugate. Now what is this? This is nothing more than the convex conjugate of the 1 norm evaluated at this point. Right? It's the maximum I can make the inner product with this point in beta, the difference between that and the 1 norm of beta. It's the convex conjugate of the 1 norm evaluated at this point, which we know is equal to minus lambda times, what is it for norms? It's the indicator of this point being in the dual norm ball of radius 1. So it's the indicator of x transpose u over lambda having dual norm of the 1 norm less than or equal to 1. What's the dual norm of the 1 norm? It's the infinity norm. So just reading off my rules, that is this whole term is just minus lambda times the indicator that the dual norm of this point is less than or equal to 1. So there we have actually the Lagrange dual function. It was not hard. Didn't require kind of taking subgradients, finding this out. And this was just a quadratic, so that part was easy. So in other words, let's write the dual problem. The dual problem is to maximize over all points u, the sum of these two terms. And I'll just put the first term in the criterion, and I'll ignore this constant. I don't need to keep this constant around, because if I'm looking for the dual problem, I can drop this. The dual problem is to maximize this, and it's actually this minus the lambda times the indicator function, that x transpose u over lambda has infinity norm less than or equal to 1. But what role does that play in terms of a minimization problem? That just adds a constraint. That adds the following constraint. I've just moved lambda up to the right-hand side of this inequality here. And I've said that subtracting off the indicator function is no more than just putting a constraint in the problem. Okay, because when this does not hold, I get a minus infinity in the criterion. And when it holds, I get a 0. So it's the same as putting a constraint there. Okay, so there's the Lasso dual. And now that we knew conjugates, actually wasn't that hard to derive. Right? Just required recognizing actually the trick that we have to substitute in z for x beta in the loss, and then just kind of continuing through the standard workflow for forming the dual function and recognizing this part as the convex conjugate of the 1 norm. So there we have it. I've written on the slides, I've just written this in terms of a minimization problem, right? Because maximize the negative of the norm of y minus u squared is the same thing as just minimizing y minus u squared, subject to this constraint. So let's just read off a bunch of kind of facts now about the dual. Well, Slater's condition holds. Why? Because we actually took the dual of this problem, this equality constraint problem, and it's convex, and clearly Slater's condition applies because there are no inequality constraints, so Slater's condition certainly applies, which means that we have strong duality, and it means that actually the optimal value of the dual and the primal problems match. Okay, but caution. Here's a kind of a word of caution that you should think about when you derive this dual. Does that mean that if I solve this minimization problem, and I took the optimal value of y minus u star in norm squared, and I compared it to the Lasso criterion here, that they should be equal? It doesn't actually, right? Because what we did is that we derived the dual problem here, which is a maximization problem, and then we threw out a constant term, which was the norm of y squared, and we flipped its sign, and we got an equivalent dual problem, which is this one. And no longer does that have the property that the value, the optimal value of this criterion is going to match the optimal value of the primal problem. Now that doesn't really, it shouldn't really bother us, because we haven't changed the solution, which is typically what we're interested in. But if we're computing the duality gap, say if you're using it for a stopping criterion for an algorithm, we have to remember that we actually have to evaluate the original dual criterion, not the modified one that we ended up at, because that's what matches f star at optimality. Okay, so that was the first fact. The second fact is this idea of gathering primal solutions from dual solutions. Let's suppose you're able to solve this constrained problem. Minimize the norm of y minus u squared subject to x transpose u, have infinity norm less than or equal to lambda. Now, why might you solve that instead of the Lasso? Well, maybe we won't get there just quite yet, but one reason could be that, for example, this problem has n variables and the Lasso had p variables. So this has fewer variables than the Lasso problem, say. Okay, so it could be favorable if n was a lot smaller than p. Let's suppose you just wanted to solve that problem. You had a nice algorithm for that problem because you worked hard at this problem. What would you do? Well, you're not really looking for u star in terms of your statistical problem. You want to know beta, right, or x beta rather, the fit. So if we go back to the stationarity condition for this that relates these two, then it tells us that beta in z must minimize L of beta z and u star. So the optimal primal solutions must minimize the Lagrangian once I stick in my dual solution. And it's actually more convenient to look at the z block here. So I can just take a gradient of the Lagrangian with respect to z and set it equal to 0. So if I do that, it pretty much recreates what we did up here. Right? It really just recreates what we did up here. So if I take the gradient of the Lagrangian with respect to z, and I set it equal to 0, then you can see after just, this in fact just repeats this calculation, we get that z must be equal to y minus u star at the solution. And in other words, I must have, because z and x beta star are equal at the solutions, I must have x beta star being equal to y minus u star at the solution. So here it is. This is how we get the kind of predictions out of the Lasso problem if you had solved the dual. I would tell you, here are the predictions you make at each x point, having solved the dual problem. It's the primal dual relationship. Questions about that? Okay, so this example revealed a bunch of stuff. It was an example of how to derive a dual for an unconstrained problem. It was an example of strong duality and stationarity, giving us an explicit relationship between the primal and dual solutions. It was an example where we derived the dual, but then took an equivalent dual, just for simplicity, and just acknowledged that even though this hasn't changed the solution, it changes the optimal value of the problem, so we shouldn't try to equate the optimal value here with that of the original problem. And lastly, it displayed the role of conjugates in the derivation of dual problems. And I'm going to completely skip this picture. I know it looks kind of exciting, but I think given the fact you guys neglected to hear the uniqueness, proof, I'm cranky and I'm just going to skip this. So, I'm just kidding. It's just that this was kind of a tangent that if we had time we could get to. But for now, just think of it as an interesting looking picture. Let's just go to the conjugates and dual problems relationship, because I want to make sure to go through this thoroughly before we finish. Conjugates pop up frequently in the derivation of dual problems. Why? It's simply because by the definition of the conjugate, the negative conjugate of f is equal to the minimum over all x of f of x minus u transpose x. All I've done is I've taken the negative on both sides of the definition of the conjugate to get this expression. And what does this look like to you? This looks like a piece that you might have in minimizing a Lagrangian. Right? It's like I have some part of my criterion, f of x, minus some dual variable times something to do with one of my constraints. So this looks like a piece of I would get in minimizing the Lagrangian over a block of variables called x. So let's be even more explicit than that. Let's suppose I give you an unconstrained problem. Minimize f of x plus g of x over all x. No constraints. How do you derive its dual problem? Well, you can do it in a couple of steps. First is we can introduce an artificial constraint. So I'm going to actually substitute x in for z here and g. And I'm going to have to then introduce the constraint that x is equal to z. Haven't changed the problem at all. Right? Trivial modification. But now I can derive the Lagrange dual function by forming the Lagrangian, which is f of x plus g of z plus u transpose z minus x. It's the dual variable I get associated with this equality constraint. And split this up into minimization over x and minimization over z because they separate. And what do you get? You get nothing more than the minimum of f of x minus u transpose x. Right? F of x minus u transpose x, which we saw was just the negative conjugate of f evaluated at u, minus the minimum over all z of g of z plus u transpose z, which is nothing more than the negative conjugate evaluated at minus u, because we had plus u transpose z rather than minus u transpose z. So in other words, here's a general recipe if you knew conjugates. The dual of a problem that looks like one function plus another is the problem that maximizes the negative sum of their conjugates, or the sum of their negative conjugates, where one function is actually evaluated at negative u rather than u. Okay, or I could also say the dual is equivalently minimize f star of u plus g star of minus u. Right, that's equivalent to a minimization problem. So that's a kind of nice, succinct relationship between conjugates and duality. And I think it's a very helpful fact to remember. It'll save you some time deriving dual problems.
What about if there is only one function, minimize fx, if the dual problem is maximize its conjugate?
No, that's not necessarily going to be true, right? Because you don't have any. There's no appearance of something like a u transpose x. So you're going to have to introduce an equality constraint somewhere. Right, the conjugate function is defined as in terms of the difference of the function in a linear term. So you need that linear term. But this is not a special case. This is the way almost all optimization problems you'll encounter look. Right? You can always chunk up the criterion into 2 bits. You can chunk it up however you want. And now we're kind of getting into something which is there's a bit of creativity involved in driving duals into how you chunk up the problem. But we'll mention that in just a few slides. So let's do some examples of the last calculation. The dual of a constrained convex problem, f of x plus the indicator function of x being the set C. So this is, again, it's constrained convex minimization, right? Because we can think of the indicator as just being a substitute for the constraint that x is in C, is, just by reading off this rule, to maximize the negative conjugate of f minus the negative conjugate of the indicator function, evaluated at minus u. And what's the conjugate of the indicator function? We know it's the support function of the set C. So there you go. That's the dual of a kind of a general form for the dual of a constrained convex problem. closely related to this, right, I kind of, we're going back and forth between indicator functions, support functions, and norms, because norms kind of are a good example of this. The dual of a problem where I have minimize f of x plus a norm is the function that is the problem that maximizes over all u, the negative conjugate of f of u, subject to the dual norm being less than or equal to 1. So there's another kind of nice general form to remember, right? Because what is the conjugate of the norm? It's the indicator of its dual norm ball. So I've just swapped out the negative indicator here with the constraint itself. Okay, so some high-level points, right? Constraints in the primal appear in the criterion in the dual, and things in the primal, like norms that are given by support functions, they appear as constraints in the dual. So their roles are switched. We saw that here with the lasso, right? That was a special example of it. If I added a norm as a penalty in the primal, it appeared as a constraint in the dual. Another special example of that. Dual cones. I'd rather get to the dual subtleties. Let's skip over the dual cones. I may come back to that at the start of the next lecture, or maybe when we talk about the second order method unit, because we'll deal with cones. But I'd rather get to this because this is probably the most important philosophical point. And we've said it already, but I wanted to repeat it and give you a few more suggestions, which is that oftentimes we'll transform the dual into an equivalent problem and still call it the dual. But beware that under strong duality, even when strong duality holds, the optimal value of that problem is not necessarily going to be equal to the optimal value of the primal, right? Because I could be removing constants from the dual. I could be transforming the dual with a variable transformation. I could be changing it from maximization to minimization. And the solution won't change, but the criterion value at optimum will. And so I cannot compute the duality gap on that transform problem. I have to recall whatever the original dual criterion was. And this is also another important philosophical point, which is that a common trick for deriving duals, which you're going to see all the time in the literature and yourself when you look at unconstrained problems, or problems that are just difficult. Sometimes it may just be difficult to derive the dual of your favorite problem. You introduce kind of auxiliary equality constraints in order to make your life easier. So if you write down the Lagrangian and you just have no traction because it's too hard to minimize, then you start introducing equality constraints. And your life starts becoming easier because that helps the minimization of the Lagrangian separate into separate minimizations. So that's a very kind of general trick that we apply. But a warning is that there's some ambiguity to how we do this. And different choices of substitutions lead to different dual problems. Now, of course, they're all equivalent to the primal problem under strong convexity, but some may be easier to solve than others. And so there's actually some kind of creativity or ambiguity into forming duals. An example of that, a concrete example of that, is the Lasso problem. So I decided to substitute here z for x beta. What happens if I decided to substitute actually z for beta and the L1 norm? So think about that, and as another practice for deriving duals with conjugates, instead of substituting in z for x beta in the loss, plug in z for beta in the penalty, and now have an equality constraint that z is equal to beta. We'll see you actually get a different dual. It's not the same dual as this problem. Of course, it's equivalent. It's equivalent to the primal problem, and so is this one, so they're both equivalent. But it's kind of less favorable because you'll see that the dual for that problem involves x transpose x inverse. It involves a matrix inverse. So just to get the dual, we had to actually maybe perform something that was expensive computationally. So I didn't do that for this problem because this one was kind of cleaner to write. And maybe it's more realistic we'd want to solve this. The other dual, like I said, involves x transpose x inverse. So just to solve it, we'd have to have either formed an approximate inverse or known something about x transpose x in order to do so. Okay, so there's ambiguity in how you form the dual. And that also gives you some room for I think it actually makes deriving duals more interesting, this fact. here's one last observation, which is that we've seen that the dual norm of the dual norm is the primal norm. We've seen the conjugate of a conjugate is itself a conjugate function if the function was closed and convex. How about the dual of the dual? So we've had this question pop up a few times. Here is a proof, a very simple proof. Actually, I didn't give you the other direction. Here's one half of the proof that the dual of the dual for this problem is indeed the primal. So let's consider a general minimization problem with linear constraints. So minimize any function you want subject to ax less than or equal to b and cx is equal to d. We can form the Lagrangian, and we can go through the kind of typical derivation of the dual. And all we have to do is we pull out here all the terms that involve x. And look, that was f of x plus some vector transpose x. And so if I minimize this over all x, I get the negative conjugate of f evaluated at the negative of this vector, just by definition of the conjugate. That's this term in the dual function. And then the other terms that involve u and v just carry straight down because they don't have any role in the minimization. So here's my dual problem. Okay, again, nice kind of use of conjugates. It's not hard to show if f is closed and convex using the property that, therefore, in that case, f star star is f, that the dual of this problem is the primal. It's just the reverse of these arguments. So just form the Lagrangian and go through the same sequence of arguments. And you'll be taking now, you see a conjugate of f star. But the conjugate of f star ends up just being f. And so you get back to this problem. I think that's also one of the homework questions, if I'm not mistaken. Okay, going the other direction. So for this class of problems, we actually do have the fact that the dual of the dual is the primal. What about in general? What if we didn't have linear inequality and equality constraints? So that was something that I was asked a couple of years ago or something, and I didn't know the answer. And so this is an example of how the Rockefeller book is very useful. Rockefeller had it on like one line of chapter 29 or something in his book, that it is true that the dual of the dual is the primal, as long as all of these functions that you're looking at are closed and convex. So for a convex problem, all we need to do is place an additional constraint that the inequality constraint functions and the criterion itself are closed. And remember that, like, a sufficient condition for that is just continuity. So pretty weak. As long as you have continuous functions in your criterion, then the dual of the dual is indeed the primal problem. And the proof of this is actually quite interesting. It's using what's called bifunctions. So if you're interested in that stuff, you can go to the Rockefeller book. But this should satisfy you, right? You're not going to be able to, there's not an infinite loop, right? You can't create the dual of the dual and get another problem, and then keep taking duals and get some kind of infinite class of equivalent problems. It's going to end after one dual. Maybe it means it's less work for you, right? Just take the dual, and then that's about all you have to explore. That was it for duality. Unless there are questions, we'll just close up the chapter on KKT conditions and duality, and we'll come back on Thursday with Newton's method. OK.